Hello everyone, MK here. Hope all of you are practicing number theory sums, Olympiad level. All Olympiad examinations starting from next month, National, International Maths Olympiad. Congruency plays an important role in cryptography that I told you earlier, but it plays the most important role for you in qualifying Olympiads. So all of you learn this topic properly. So many problems are there. So many different types of problems are there. So many theorems are there. But once you are into this topic, then hardly you will like to solve sums from other topics. And this will pay you in all competitive examinations. Number theory is an integral part of it. Concept of integers is an integral part of it. In the last session, I have explained Fermat's theorem and some of its application, how it can be used to solve problems from number theory. This session, I am going to generalize Fermat's theorem. What is the generalization of Fermat's theorem? Actually, we don't have the scope to learn theory in details here, because theory proving is not required, but knowing how you arrive at that conclusion where a theory is valid, that is important to know. I wanted to prove all, but the problem is before starting linear congruency, I am not going to give you proof of any theorem. Instead, I will explain and you will find easy application in solving problems in this session as well as in Olympiad papers. Okay, so let us start Euler's phi function and Euler's theorem. Then we will learn Wilson's theorem, and then we will find some common application of congruencies. Actually, there is no end of congruency. Such a important, such a useful topic. Even I am solving all the sums till the date I know, that will not be enough. Somebody has created another problem for you. So you cannot plan all the problem, but you need to know the theory and its application in solving problems. Okay, so let us start. So I will be stating what is Euler phi function first. What is Euler phi function? It is written as phi n. Phi n. What is Euler phi function? So this one is a function. Why this is a function? It's like function, it will give us values. That's why it is called function. It is a function from set of natural number to the set of natural number only. But those who don't have the idea of function concept, they will obviously not be able to understand the way I tell you. Those who know function, they can keep this concept in their mind, but it will not give you any extra advantage. Okay? So you are going to find number of positive integers less than or equal to n that are relatively prime to n. Phi n stands for that. Two numbers are co-prime if their greatest common divisor is 1, that you know. Based on that, if we wish to find phi 10, how many numbers are less than 10 and prime to 10? That is obvious. 1 is a number which is prime to 1. 1 is a number which is prime to 10. 3 is a number prime to 10. 7 is a number prime to 10. 9 is a number prime to 10. In between, 2 is not prime. In between 4, 5, 6, they are not prime to 10. Even 8 has a common factor with 10. So 8 and 10 are not co-primes. Okay? So phi 10 equal to 4. What is phi 1? What is phi 1? I'll not remain silent about phi 1. We'll write by definition phi 1 equal to 1. Okay? What is phi 2? Phi 2 will be equal to 1. What about phi 3? Phi 3, there are two numbers less than 3 and they are co-prime to 3. That is 1 and 2. So phi 3, number of those co-prime numbers prime to 3 are 2 in number. You understand? When you write number of numbers less than 3 and prime to 3, what are they? They are 1 and 2. What about phi 4? What are the numbers? Those numbers are 1 and 3. So it will be 2. Isn't it? Phi 4 equal to 2. What about phi 5? How many numbers are there? If you count, it will be 1, 2, 3 and 4. All numbers less than 5. So phi 5, number of numbers less than 5 and prime to 5 is equal to 4. If you go by phi 6, then it is going to be different. Isn't it? Phi 6 how many? Phi 6, those numbers will be 1, 5. Only 2. There is no pattern over there. But once you start finding phi 7, this is 6 in number. So automatically, for a prime number, we can fix it. For a prime number, we can do it easily. What is that? For a prime number, it will be this. We can write in the form of theorem. What is the theorem? If P be a prime number, then phi P will be equal to P minus 1. Okay? Prime number phi P. So phi 37, all numbers less than that are prime to 37. That is 36. Phi 73, all numbers less than that will be prime to it. 72. So regarding prime number, everything is clear. Let us know numbers of this form. Then we will generalize. Theorem 2. Let a number be of the form n equal to p to the power k. Then phi n, p is a prime number and n is a positive integer. P is a prime number and k is a positive integer. Then phi n or phi p to the power k going to be p to the power k 1 minus 1 by p. How? How to write this? This, if you simplify, it is going to be p to the power k minus p to the power k minus 1. Number of primes less than p to the power k and prime to that will be p to the power k minus p to the power k minus 1. If n is equal to p to the power k. I can give you a simplified proof because this proof sometimes help you to solve problems. So which is within our reach, that proof we can always think. What is the proof that phi n phi p to the power k is p to the power k 1 minus 1 by p? I am telling you one thing. Number of numbers which are not prime to p to the power k and less than that will be p to the power k minus 1 in numbers. So prime to that will be p to the power k minus that. You understand the logic? I am telling that number of numbers less than p to the power k and not co-prime to p to the power k is p to the power k minus 1. So number of numbers less than p to the power k and less than p to the power k and prime to that will be p to the power k minus p to the power k minus 1. Clear? How? Okay, if it is not clear, then let me try my level best to explain it to you. I will be writing all the numbers from 1 to p to the power k. I am writing in this particular manner: 1 to p minus 1 and last one is p. I am writing in every row p numbers. So next one starts with what? P plus 1, p plus 2, p plus p minus 1, and this is p plus p. P plus p means 2p. Next one starts with what? Another p will be added. 2p plus 1, 2p plus 2, and next one 2p plus p minus 1, 2p plus p. Okay? This way, if we go for last row, which number will be there? Last row I am going to write. Obviously, the last digit is going to be, this is what? You just write, this is 1 into p, no? This is 2 into p, no? This is 3 into p. So here, the last element going to be what? P to the power k minus 1 into p. That is p to the power k. So where does it start from? It will start from p to the power k minus 1 minus 1 into p plus 1. Then p to the power k minus 1 minus 1 into p plus 2. No problem if you don't understand. Believe me, I just wanted to tell you the proof. It is very interesting for me. That's why I am writing the proof. If you don't understand, don't do it. But those who understand, please try to pay attention. It will be p to the power, I will explain again, p to the power k minus 1 plus p minus 1 dot 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 this manner. Okay, I did not write all the terms. Clear? No, this is actually continuation. There is no dot dot. Just I am writing p elements in each row, isn't it? So every row, these last elements, 1 into p, 2 into p, 3 into p, p to the power k, these k minus 1 elements are, all these elements are prime to p to the power k. No, they are not prime to p to the power k, they have a common factor. Okay? So how many elements there are common factors over there? Every time you will get that p, total number of numbers is p to the power k, that is given only. Out of these p to the power k minus 1 numbers, they are prime. These p to the power k minus 1 numbers, they have common factor, not prime. They are not co-prime. They have common factors. So 5p to the power k will be apart from those. This last element you can see here, no? Last element, all the elements you see. P, 2p, 3p. Can you see this? So number of these numbers will be how many? It will be p to the power k minus 1. These p to the power k minus 1 numbers, they have common factors with p to the power k. But apart from those numbers like p plus 1, it has no common factor. 2p plus 1, it has no common factor. This one has no common factors. So if we remove those numbers which are not prime to p to the power k, the number of numbers prime to p to the power k will be remaining p to the power k minus p to the power k minus 1. Clear? That's why we are writing phi n equal to phi p to the power k, p to the power k minus p to the power k minus 1, and if we take common, it will be p to the power k 1 minus 1 by p. Okay? Clear? You understand? Now tell me what will happen if it is p1 to the power k1, p2 to the power k2, pn to the power kn. To find Euler's phi function for this, we need to know another theorem which is beyond the scope of proving it. Okay? That is phi m into n will be phi m into phi n. Actually, proving will interrupt also our progress for Olympiad sums. But you have to understand all these things by examples, by many examples, so that confidently you can apply this. Now by fundamental theorem, if those primes are taken p1, p2, pn and their indices are k1, k2, kn respectively, then phi n will be equal to this number n itself, or one thing you can write, phi n means, by using this property, multiplicative property, you can write phi, this can be extended for 3 numbers also. Suppose phi m n l there, this can be written as phi m, phi n into phi l. So here also phi n will be phi p1 to the power k1, phi p2 to the power k2, this way phi pn to the power kn. Okay, so this will be p1 to the power k1 into into 1 minus 1 by p1, p2 to the power k2, 1 minus 1 by p2, like this. So if you multiply this, all these, n is coming over there, 1 minus 1 by p1 into 1 minus 1 by p2, it continues this way. Okay? So if we have, I am taking one example now, it will be better understood by you. Suppose you want to find phi 144. 144 is what? Phi 16 into 9. Prime factorization, that is phi 2 to the power 4 3 square. This is nothing but 2 to the power 4 3 square into 1 minus half, 1 minus 1/3. So this is 2 to the power, 144 into half into 2/3. So it is 144 by 3. This is 48. So 48 numbers are there less than 144 and they are all prime to 144. Any number you can do this way. Okay. So how many theorems you have learned here? 3 theorems. That number 1, phi p, p minus 1. Then if it is p to the power k, it will be p to the power k 1 minus 1 by p. And the theorem that phi, this also you can state as theorem. Now actually this is continuation of previous theorem 2, but still you write because we are proving it and will be using in solving problems. So if it is phi n, that number which is composite prime factorization is possible, its number of primes less than n and prime to n going to be by this formula and this multiplicative property. And the most important theorem is here that we are going to do now, that is Euler's theorem. I told you I will not give you the proof of any theorem now. So long linear congruency is not done in details, no proof is required. Okay? We will do linear congruency, Chinese remainder theorem, then we will come back to proving of all these. And binomial theorem also, because we have many proofs by using binomial theorem. So now what is Euler's theorem? This is very interesting, very important, and I told you this generalization of Fermat's theorem. Fermat's theorem is true for prime numbers only, isn't it? If A is prime to P and P is a prime number, a to the power P minus 1 congruent with 1 mod P. This theorem, that Euler's theorem, I am going to do, it is true for Fermat's theorem as well as true for any integer. Only condition to be maintained here that integer and n are co-prime, and then we can state that a to the power phi n is congruent with 1 mod n. I am just writing the general case, then you will be able to understand. Let n equal to p. Let n equal to the prime number. Then the theorem stands for what? A to the power phi p congruent with 1 mod p, isn't it? Phi p is what? Just we have got in a theorem. What is phi p? How many prime numbers are there less than p and prime to p? That is p minus 1, isn't it? So there it will be a to the power p minus 1 congruent with 1 mod p. This is Fermat's theorem. We have used it to solve many problems by remembering that it will be prime. Like 37 to the power 23 minus 1 also, we can say that it is 1 mod 23. Okay? That is when 37 to the power 22 divided by 23, the remainder is 1. Such a huge sum can be solved in one step. But if we want to write, say, 37 to the power number, suppose we have, let me find the value of phi 15. Say I am taking n equal to 15. Okay? We are writing n equal to 15. How many numbers are there? You can write, or you can use the commutative property. I mean that multiplicative property. Here it is going to be what? 1, 2, 4, not 5, not 6, but 7, not 9, but 8, 10, no, 11, then 12, 13 and 14. How many? 9 numbers we got. Check once more. No, 12 not possible because 12 has a common factor. So 5 15 is 8. You can get it by other method also. You try to avoid this counting. It is 5 3 into 5 5. Okay? 2 into 4, that is 8. This 8 is not prime number. See, by using Euler's theorem, how easily we are getting it. Say we want to find, say, I just noticed that phi n and a only co-prime numbers. Like somebody want to write 31 to the power 8. This will be congruent with 1 mod 15. Why 1 mod 15? Because 515 only you got 8. So that will come here. If you notice the theorem, it is a to the power phi n is congruent with 1 mod n. So 31 to the power 8 should be congruent with 1 mod 15. Why? Because I have written 31 to the power 515 is congruent with 1 mod 15. 515 is 8. So 31 to the power 8 is congruent with this. You see, this 8 is even number, and in that case it was a prime number. For prime number it is valid, which gives the statement of Fermat's theorem only. But this is true for even numbers also. That's why I told you it is generalized Fermat's little theorem, Euler's theorem. Okay? Both are great mathematicians. Euler spent his life solving maths only, inventing so many things in mathematics. Fermat, although he was a lawyer, he was a specialist mathematician in the field of number theory. Okay? In his free time, periodic Fermat used to solve number theory problems. I cannot put one above the other. Although Euler's contribution in mathematics is more than Fermat's, but Fermat, what he gave in number theory only, that can be done by genius only. Okay? So Euler's theorem, remember this way, it is generalized Fermat's theorem. But why do you remember then differently? Only Euler's theorem will be good? No. We'll save our time by using Fermat's theorem. If prime number is there, very first we can reach this conclusion. In Euler's theorem, you need to find phi n. Then only a to the power phi n will be congruent with 1 mod n. You agree with me or not? You think? And before we proceed to solve problems based on it, I will tell you to solve, to find phi of something. You just find phi of 32. Just take 1 minute's time to decide yourself. Okay? If it is done, keep this thing ready. Phi of 240. Just practice before you start. And these sessions you are practicing with me. I am doing it here. You are doing it. You are doing it from your home. Okay? Then only it will be useful. If you don't do that, no, it will not be useful for you. Because no one can memorize anything. No one can memorize everything. Okay? So do it with me. Now only. Phi 32 you write. It's very easy. Phi 32 is phi 2 to the power 5. We can write it very first. 1 minus half. So 32 by 2, 16. Phi 240, how do you write? Phi 240. This is, it is divisible by 16. It is divisible by 32 also? No, 16. 16 you write. 16 into what? 1, 5. So this is nothing but 2 to the power 4, 3 to the power 1, 5 to the power 1. Going to be into 5 to the power 1, 1 minus half, 1 minus 1/3, 1 minus 1 by 5. So 240 into half into 2/3 into 4 by 5. Simplify it. 8, 64 in number. 64 numbers are there less than 240 and prime to it. Okay. Do this one. 5 to the power 48 is divided by 12. 12 is not prime number. So Fermat's theorem is of no use. Let us apply for this kind of sums. Let us try to apply Euler's theorem. It is generalized one and it will help you a lot. I am sure it will help you a lot. Try. Find the remainder when 5 to the power 48 is divided by 12. See the approach? Here I am going to apply. Let us find 512. 512 is what? 5 2 square into 3 to the power 1. 2 square, 3 to the power 1, 1 minus half, 1 minus 1/3. This is 12, half, 2/3. So this is equal to 4. Okay. So 512 is 4. We can write, what we can write? 5. 5 is any number which is co-prime with 12. A is co-prime with n. Then what Euler's theorem state? A to the power phi n is congruent with 1 mod n. A to the power phi n is congruent with 1 mod n. So let us take n 12. Here you take A equal to 5, n equal to 12. So 5 to the power phi 12 congruent with 1 mod 12. Phi 12 just found, it is 4. This is congruent with 1 mod 12. How to get 5 to the power 48? Am I correct? So how easily it's coming? 5 to the power 48 is equal to, is congruent with 1 mod 12. Obviously you can do it by using congruency only, but I wanted to show you the beauty of Euler's theorem. And this is a very simple problem which you could have done by using plain congruency concept, simple congruency concept. But sums are there where you cannot use common congruencies one. Okay, go for next one. Oh my God, this is 35 to the power 33 is divided by, I am writing here, 35 to the power 33 mod 24. You have to find. This is the question. 35. If we have planned to use the Euler's theorem, then we'll go for finding phi 24 first. What is phi 24? It is phi 8 into 3. This is phi 2 cube 3 to the power 1. So this is 2 cube multiplied by 1 minus half, 1 minus 1/3. 8 into 3 into half into 2/3. Answer is 8. So does it help? You have to think. If you write by taking A equal to 34, and we find that 35 and 24, they are co-prime. GCD is 1. So a to the power phi n is congruent with 1 mod n. What value of n you have taken? We are going to take n equal to 24. So a is 35. 35 to the power phi 24 is congruent with 1 mod 24, because my aim is to divide by 24. That's why I am calculating phi 24 here. 35 to the power phi 24 is 8, congruent with 1 mod 24. But we need 35 to the power 33. How to get 35 to the power 33? You just do by raising the index to 4 on both sides. One to the power 4 mod 24. Therefore, 35 to the power 8 into 4 is what? 32. This is congruent with 1 mod 24. But we need 35 to the power 33. So property of congruency is required here. We multiply both sides by 35. Then we get 35 to the power 33. So on multiplying by 35 on two sides, multiply by 35. So 35, this is congruent with 35 mod 24. Okay, so 35 to the power 33 congruent with mod 24, but 35 is greater than 24, so we must divide once mentally. This is equivalent to say 11 mod 24. Clear? So 11 is the remainder when you divide 35 to the power 33 by 24. Such a huge number. Okay, let us do this one. Show that n to the power 18 congruent with 1 mod n. How to prove this? N to the power 18 congruent with 1 mod n. What is the easiest way to get it? Think before I do it here. No way. N is a natural number, and you want to show that n to the power 18, oh sorry, not n, it is 9. This is 9, sorry, extremely sorry for that. N to the power 18 congruent with 1 mod 9. So like previous one, here you will write phi 9 first. Phi 9 is what? 9 into 1 minus 1/3. It is 3 square. So 9 into 2 by 3, this is 6. So n to the power 6, you will write phi n, no? N to the power, for any integer, it's 18 power. When divided by 9, remainder is 1. Any integer, there is no choice for it. So n to the power phi n is congruent with 1 mod 9. So this implies n to the power 6, 1 mod 9 raising the power to 3. Raising the index on both sides to 3. What do you get? Congruent with 1 cube mod 9. So n to the power 18 congruent with 1 mod 9. Isn't it? Do this one. This is a very good problem. I have seen in previous Olympiad papers. May not be this one exactly, but this kind. Prove that n to the power 6 minus 1 divisible by 504. There is a problem here because 504 it's huge. 5 of this is not equal to 6, never. Am I correct? N to the power 6 minus 1 is divisible by, instead we can start this manner. Let us find the factors of 504. Can we find the factor? Try once. Of course we can find. 6 is a factor. Then this is divisible by 84. 84 4 into 21, isn't it? That is 4 into 21. So write all these. You get in terms of, this is 7, 3, getting a 3 here also, 9 and then 8. Okay. If you can prove that n to the power 6 minus 1 divisible by 9, n to the power 6 minus 1 divisible by 8, n to the power 6 minus 1 divisible by 7, then it is done. N is a prime greater than 7. So this is prime. We can use, if required, Fermat's theorem. We can use Euler's theorem. You can use common congruencies also. Am I correct? You try, take 1 or 2 minutes time and then I will solve it. Try. With 9, how do you operate? Phi 9 you find. Phi 9 is what? Just found. It is 9 into 1 minus 1/3. That is 6. Therefore, n to the power 6, n to the power 6 congruent with 1 mod 9, isn't it? So n to the power 6 minus 1 congruent with 0 mod 9, clear? Therefore, this you write n square cube minus 1 n square minus 1 n square plus 1 congruent with 0 mod 9. Am I correct? I have done the factorization over there, n square minus 1. Okay? So if you can prove that, it is proved that divisible by 9, isn't it? 9 divides n to the power 6 minus 1, this is proved. N to the power 6 minus 1 is on left side. Can you prove anything else? N plus 1, n minus 1 is congruent with 0 mod 9. So divisibility by 9 is ensured. The number n to the power 6 minus 1 ensued, and from there we are getting this. Now if you can prove that this thing divisible by 7, it is done. This thing divisible by 8, then also it is done. Is this thing divisible by 7? I think it is always true. N to the power 7 minus 1 is congruent with 1 mod 7. So n to the power 6 minus 1 congruent with 0 mod 7. So this one ensures that n to the power 6 minus 1 divisible by 9 and divisible by 7. We have used Fermat's theorem there. We have used Euler's theorem here. This is by Euler's theorem. Euler's theorem. And this one by Fermat's theorem. What about the next one? With 9, with 7 done. How to deal with 8? I told you there is no restriction that I have to use Fermat's theorem, Euler's theorem only. Any other convenient method is there, we should try. When n to the power 6 minus 1 is the matter of concern, we can, this is n to the power 6 minus 1 only, then we can test divisibility by 4. Numbers are of the form, this since n is given a prime number, so prime numbers are of the form what? N equal to 4k plus 1. Prime numbers of the form what? 4k plus 3. Isn't it? If you can prove that this thing divisible by 8 under this consideration, then it is done. As well as under this condition, then it ensures that it will be divisible by 8. You understand? We have proved divisibility by 9, we have proved divisibility by 7. Here we are going to prove divisibility by 8. For that, n to the power 6 minus 1, I have expressed this form. Now, in this case, when n equal to 4k plus 1, n plus 1, n minus 1, this is what? 4k plus 2. It's big one. I am not writing, and it will not be divisible by anything. Just leave it there. Here it ensures that this thing divisible by 8. Okay? For n equal to 4k plus 3, you check with this only. n4 plus n square plus 1, no. Just put it here. It is 4k plus 4, 3 plus 1, and this is 4k plus 2 n to the power 4 n square plus 1. This thing again divisible by 8. So prime number of any form 4k plus 1, or all prime numbers are of the form either 4k plus 1 or 4k plus 3. We have done it before. So if it is true for 4k plus 1, the number divisible by 8, and for 4k plus 3 also, then this thing is divisible by 8. So what have we done? These numbers are co-prime. What numbers? Those numbers 7, 9 and 8. So n to the power 6 minus 1, you have proved that it is divisible by 7, it is divisible by 9, now it is divisible by 8. Therefore, n to the power 6 minus 1 is divisible by 7 into 9 into 8. That is 504. Done? It's a nice sum. You must try again yourself after 2 days, not today. Today you will be able to do. After 2 days, if you remember, then it's okay. You will remember forever. You'll never forget. Okay? Now Wilson's theorem. Read the theorem. This provides a condition for a number to be prime. See? Checking primality by Wilson's theorem. Yes, can be done, although there are some restrictions. But restriction means numbers cannot be very large. Then it's finding factorial will be very difficult for us. At least smaller prime numbers, their that -1 factorial plus 1 factorial of p minus 1 congruent with -1 modulo p. What do you mean? It means that this implies that p minus 1 factorial plus 1 congruent with 0 mod p. Okay? P minus 1 factorial plus 1 congruent with 0 mod p. So any factorial, just let us take, this theorem checking, this is universal truth, that it will be always divisible by p. P minus 1 factorial plus 1 divisible by p. But if somebody asks you to verify with a prime number, say verify means LHS is equal to RHS, with this prime only, say 131, we take 79 only. Calculating 79 factorial will be very difficult. LHS is equal to RHS you cannot prove. But by taking p equal to 79, you can easily say that 79 minus 1 factorial plus 1 congruent with 0 mod 79. That is factorial 78 plus 1 is divisible by what? P is the prime number, then only divisible by 79. And another very interesting thing to note, this converse is also always true. P minus 1 factorial plus 1 congruent with 0 mod p, this is true. Converse, if this is true, then p must be a prime number. Okay? Wilson's theorem states that, its converse states that if p minus 1 factorial plus 1 is there and is divisible by p, then p must be a prime number. We will find the application only. Let us go for these simple applications one by one. Learn it today and apply it in solving good problems. Okay? Show that factorial 18 plus 1 is divisible by 23. How will you start? Factorial 18 plus 1. Start once, try once, then I will try to give you a proof of this theorem by taking one example which is very interesting. First you try that to prove that factorial 18 plus 1 is divisible by 23. There is no relation between 19 minus 1 and 23. This is the main problem here. Am I correct? So how to prove? Let us start with Wilson's theorem only. We have factorial 22. I mean 23 minus 1 factorial plus 1 congruent with 0 mod 23. So 22 factorial plus 1 congruent with 0 mod 23, isn't it? This thing divisible by 23. To prove that, we got this thing. 22 factorial plus 1 congruent with 0 mod 23. You start writing this thing like 22 factorial this manner. 22 into 21 into 20 into 19 into 18 factorial plus 1 congruent with 0 mod 23. This 22 you write 23 minus 1. This you write 23 minus 2, 23 minus 3, 23 minus 4 into 18 factorial plus 1 congruent with 0 mod 23. You can see that this thing divisible by this thing and their product divisible by 23. If you open all these 4 brackets, then how many terms will be there? 8 terms going to be there. Out of them, except this thing, minus 1 into minus 2 into minus 3 into minus 4, out of those 8 products, except this one product, everything divisible by 23. So into 18 factorial plus 1 congruent with 0 mod 23. You agree? This implies, this is what? This is 2, 6, 24. 24 into 18 factorial plus 1 0 mod 23. Am I correct? Or 23 plus 1 into 18 factorial is congruent with minus 1 mod 23. You add 23 to the power 18 or subtract as you like, because this thing divisible by that, no? So this implies that factorial 18 is congruent with minus 1 mod 23, and this proves that plus 1 congruent with 0 mod 23. Clear? So this thing is divisible by 23. It is proved. Try next one. All this can be proved, and you are playing with factorial symbols. You think how to prove 4 into 29 factorial, how to prove 4 into 29 factorial plus factorial 5 is divisible by 31. Start. You think, then I will do. Just one very big problem I have solved. You should try this one. What to start from? 31 related. In the previous sum, 23 was related. I have started with 23 minus 1 factor. You start the same manner, isn't it? 31 minus 1 factorial plus 1 congruent with, you can write minus 1 also. It's up to you. You write from beginning. This is congruent with this theorem, you remember, congruent with minus 1 mod p. So write minus 1 mod 31. Okay. So this implies 29 factorial congruent with minus 1 mod 31. this you can write as 30. Oh sorry, this is not 29, this is 30 factorial. 30 factorial is this. 30 factorial you can write 30 into 29 factorial. See, the approach is same. Minus 1 mod 31. So this implies 31 minus 1 plus 1 you write. That looks better. Plus 1 congruent with 0 mod 31. 31 into 29 factorial divisible by 31. So minus 29 factorial plus 1 congruent with 0 mod 31. Clear? Now multiply both sides by minus sign. Minus 1. This minus 1 congruent with 0 mod 31. We have multiplied both sides by minus 1. Clear? Now multiply both sides by 4. Isn't it? So what does it prove? It proves that four into 29 factorial minus 4 congruent with 0 mod 31. Now see the proof. They have asked you to prove factorial 5. How to reach factorial 5? Factorial 5 is what first you think? 120. So how to get it? And it will be plus factorial 5. Okay? How to get that? You have to realize factorial 5. 4 into 29 plus factorial 5. So for that you add 124 on both sides. Okay? So this implies 4 into 29 factorial plus 124 mod 31. What is the advantage? You almost got. 4 into 29 factorial, 124 minus 4 is what? This is congruent with mod 31. This is factorial 5. (124) divisible by 31. So it will be 0 mod 31. It's correct? Done? Hope you have understood. Go for another one. P be a prime number. Prove that 2 into p minus 3 factorial plus 1 congruent with 0 mod p. How to prove it? P be a prime number, you prove that like previous sums only. What we did? This time you must try to do it. Try. 2 into p minus 3 factorial plus 1 congruent with 0 mod p. Again, here when you are going to use Wilson's theorem, you see this part. This part has no direct link with p minus 3 factorial or 2 multiplied it. So what you will do here, you will write p minus 1 factorial congruent with minus 1 mod p. Okay? You can write this p minus 1 factorial congruent with minus 1 mod p. Now like previous sums, go on expanding it. How long? We need p minus 3. Till that, congruent with minus 1 mod p. Am I correct? Again that product. P, how many are there? How many terms are there if you open the bracket? 4 terms. Out of those, you expand it, you write once. If the previous sum is not clear, it will be clear then. Isn't it? See, this is divisible by p, this part divisible by p. So you can remove it from there. So 2 into p minus 3 factorial congruent with minus 1 mod p, and hence the proof. Okay, so it is not difficult. Wilson's theorem is not difficult to apply. You can play with factorial by Wilson's theorem. Do this one. In this sequence, let it be the last one. Factorial 22 plus 254 is congruent with 0 mod 23. How to prove it? This is not a difficult one. Everyone can try before I do it here. I told you to look at this term always and then use Wilson's theorem. This is a prime number. So 23 minus 1 factorial, 23 minus 1 factorial is congruent with what? Minus 1 mod 23. So 22 factorial congruent with so this implies 22 factorial plus 254 congruent with 254 minus 1 mod 23. We have added 254 on two sides. This is what? 253 mod 23. This is completely divisible. 0 mod 23. So this one is proved. So easy. Okay? Not all sums will be similar, but basic approach of using Wilson's theorem is that only. Note under mod what is there. Write the theorem based on that and then proceed. Now I am asking you some questions which after finishing Fermat's theorem, Wilson's theorem and Euler's theorem to prove these kind of things. These are from old Olympiad papers. Positive integer is of the form 10a plus b. Prove that n divisible by 17 if a minus 5b divisible by 17, n is divisible by 19 if a plus 2b is divisible by 19. How will you proceed? Will you apply Wilson's theorem? A and b are integers. Okay? N is also integer. Positive integer n. This is n is there. N is of this form 10a plus b. Prove that n divisible by 17 if a minus 5b divisible by 17. Do you need any theorem or just congruency? You think? You just try first, then I'll do. 10a plus b, prove it. I find another interesting sum for you. Prove it first. Is it possible? You can write, no, n. N is what? 10a plus b. 10a plus b. We need to write that form. So this 10a plus b, can't you write this form? A minus b form, a minus 5b form. 17 is required, no? So we write this one 17a, 17 into a plus b. I am writing. Then I am subtracting also. What we are going to subtract? What we are going to subtract? 10a, it will be minus 7a plus 16b. No, it has not come. Then what to do? We have to get it of the form a minus 5b only, no? A minus 5b divisible by 17. But we haven't reached it. So 10a plus b, 10a plus b, we'll write multiple of 17 plus something. What? Think. Similar is the sum here. N is divisible by 19 if a plus 2b is divisible by that. Okay? A plus 2b divisible by 19. But how to prove this one, that a minus 5b is divisible by 7? Then it is divisible. 17a you can separate if you don't write this manner. No theorem will work. First, let me tell you clearly. If you write this thing as a minus 5b, we are writing this minus 7 into a minus 5b, and here you are writing 34b. Okay, this we are writing 34b, minus 34b. So 35, no, this thing we have to adjust. What can we write here? Minus 7a we have written. This is just manipulative. It will be 17a and this thing 34b. No, minus 34b. Sorry. It is minus 34b. So this is 17a minus 2b minus 7a minus 5b. So this thing divisible by 17. If you can prove that this is divisible by 17, then it is done. Just that only. Because 7 is not divisible by 17. 17 does not divide 7. So 17 must divide a minus 5b. Then only this whole number will be divisible by 17. Okay? How to prove this? Can we ask this question? Now it is in various forms. Okay, by taking values in that. N divisible by 9 if a plus 2b divisible by 19. How to prove that? This was the first part. Second part is here. How to apply it? Again you have to write that N is what? 10a plus b. Try to write in terms of a plus 2b. Okay, what I am targeting here, I am writing this as 19. No, you need 19. So 9 into a plus 2b, 10a plus b plus, can you write this manner? Check once. 10a plus b plus 9a plus 2b is what? This is nothing but 19 into a plus b. This thing is divisible by 19. Okay? And 10a plus b divisible by 19. It is given, no? 10a plus b, that number, it will be divisible by 19. If this part divisible by 19, so this a plus 2b has to be divisible by 19. So that This is known, this is known, this part is also known now. Clear? Not a difficult sum. How to prove this kind of problem? What congruency helps here? Is it the application of Euler's theorem, Fermat's theorem? No, we don't need it. We just need to check here this thing 5 to the power, just let me check, it is 2 to the power, the sum is 2 to the power 5n plus 1, sorry, it is written down. 23 divides, the sum I am correcting here, so that 23 divides 2 to the power 5n plus 1, 7 into 3 to the power 2n plus 1. This is the sum. I have typed wrong. Show that 23 divides this thing. We can solve some problems. I settled these two sums just to understand that always we don't need all those theorems. Common congruency helps. Okay? For all n greater than or equal to 1 and it's an integer, we can easily prove that this is always divisible by 23. How to? You notice this term 2 to the power 5n into 2, (32 to the power n into 2, 3 to the power 2n plus 1 is what? 3 into 3 square to the power n, 3 into 9 to the power n. Are you getting something, some information from there? Check. Are you getting something from there? This 32 to the power n minus 9 to the power n is always divisible by 32 minus 9, that is 23. So this implies that congruent with 9 to the power n mod 23. Is that clear? So now you need to manipulate. Clear? You multiply both sides by 2. This implies 2 into 32 to the power n mod 23. Clear? You understand? 2 into 32 to the power n congruent with 2 into 9 to the power n. We have reached almost. Here it is 2 into 5 to the power, but here we are getting just 2. So you need to add 5 on two sides. You write, you write this thing as 2 into 5 to the power, 2 into 5 to the power n, 2 into 5 to the power 2 into 2 to the power 5 to the power n congruent with 2 into 3 to the power 2n mod 23. So we need, just simplify it, 2 to the power 5n plus 1 only was written. No, there is no point of hesitation. Minus 2 into 3 to the power 2n is congruent with 0 mod 23. Clear? This is nothing but, this we have taken on left side, so it will be 0 mod 23. But I need to get 7 into 3 to the power 2n plus 1. So what I will do there? 2 to the power 5n plus 1 plus, you write 18 into, we need what form? 3 to the power 2n plus 1. So 3 to the power 2n plus 1, you just simplify it, it will be clear. The expression you have to get 7 into 3 to the power 2n plus 1, isn't it? So this is nothing but this is 3 and this is 2. This is nothing but 7 into 3 into 3 to the power 2n. So if you get it 21 over there, then it is fine. So we add 23 into 3 to the power 2n on both sides. 23 into 3 to the power 2n we have added on both sides. So this implies what? 23 minus 2 is 21. And 23 3 to the power n divisible by this? 0 mod 23. So this one ensures that to the power 5n plus 1, 7 is congruent with 0 mod 23. Clear? This only we are supposed to prove. This thing always divisible by 23. And this is a very good problem which we have solved without Fermat's theorem or Euler's theorem or Wilson's theorem. Isn't it? Hope you have enjoyed this session. We have done the application of 3 theorems. At the end, I showed you sums can be done without those theorems also. So when you are going to solve number theory problems, do not think that I have to use this theorem, I have to use this theorem, that theorem. No. You first have the simplest approach of congruency. If it is done by that method, it's fine. Otherwise, think about those theorems. Clear? Thank you for staying with me. I hope I'll be able to take the next session on linear congruencies and Chinese remainder theorem.